In this video, we will prove this equation by adding an infinitesimal amount of helium into a gas mixture of helium and argon at constant temperature and pressure condition. The total number of moles of these two gases is denoted by uppercase N. N is PV over RT. Assuming the mole fraction of helium is X, then the number of moles of helium and argon are X times N and 1 minus X times N. After we add this infinitesimal amount of helium in the mixture, the amount of helium is Xn plus Dn. The number of moles of these two gases becomes this uppercase N. This is the previous number of moles plus Dn, the added amount of helium. The mole fractions of helium and argon change to these two different expressions, and their partial pressures are this times P and this times P. Again, pressure remains unchanged after the addition of the infinitesimal amount of helium. Now let's look at the Gibbs energy change of the entire system. There are three components. We'll calculate the Gibbs energy of the added helium and the changes of the two pre-existing gases. So first, the Gibbs energy of the added helium is this amount of helium, added helium, Dn times RT times the logarithm of the pressure of this helium over P naught. What about the change of the Gibbs energy of the pre-existing helium? It's the amount of helium times RT, again, times the pressure change, final pressure over initial pressure. Similarly, we get the change of the Gibbs energy of argon with this expression. Now, because the Gibbs energy is additive, we'll just sum up this term, and this term to get the total Gibbs energy change expressed here. We need to simplify this expression. So we're going to use the truncated Taylor expansion of this. The natural logarithm of 1 plus delta is really close to delta when delta is close to 0. And then we can simplify this logarithm to this. We can simplify this further into just the logarithm of x times p over p naught. And we can also simplify this natural logarithm here. It's just dn over x minus dn divided by this uppercase N plus dn. We further simplify the last logarithm over here. So again, we simplify the three logarithms using the truncated Taylor expansion of the natural logarithm of 1 plus delta. So after we do all those mathematical treatment, in the end we have the exact differential of the Gibbs energy of this system to be equal to dn. This is the infinitesimal amount of added helium times RT times the natural logarithm of the mole fraction of helium times P over P naught. And again, we're going to use this equation. Mu is dg over dn. Both dg and dn are infinitesimal. We do the division. In the end, we get RT times the natural logarithm of P helium over P naught. In the analytical expression of mu helium, we should have this mu superscript naught term. This is the standard chemical potential. Why don't we have this? Well, this is simply because we assumed the standard molar Gibbs energy is equal to the standard Gibbs energy of formation, and for helium, these two are just exactly 0. Therefore, mu naught is 0. So over here we have 0 plus RT times this natural logarithm, and the 0 I mentioned is simply this value of mu naught of helium.